For more than a century, one fault has owned California's nightmares. It is not the one seismologists are watching now. Months ago, government supercomputers simulated 50 possible ruptures on a fault most people outside the Bay Area have never heard of, one that runs directly beneath 2.5 million people, not empty hillsides. It is already 18 years past its own historical breaking point. New data suggests the ground itself may amplify the damage in ways nobody predicted. The strangest part isn't the fault, it's what could set it off, a trigger with nothing to do with California. That fault is called the Hayward. It runs 74 miles along the eastern side of the San Francisco Bay, straight through Oakland, Berkeley, Fremont, San Leandro, and a dozen other cities packed with people who drive over it, sleep above it, and walk across cracks in the sidewalk without knowing what those cracks mean. The U.S. Geological Survey has already modeled what happens if this fault ruptures at magnitude 7 directly beneath Oakland. The estimate: up to 800 dead, 18,000 injured, $165 billion in damage, and that's before fires that typically follow a major earthquake finish spreading through broken gas lines. This isn't speculation from an outside group. It's the government's own planning scenario, called Haywired. To put that in human terms, seismologists have described the shaking directly above a rupture like this as strong enough to knock a heavy piece of furniture across a room without anyone touching it. That's not from a distant epicenter. That's a fault breaking directly beneath the floor people are standing on. Here's why the timing matters. The last major earthquake on this fault happened on October 21, 1868. It killed 5 people, injured 30, and flattened downtown Hayward so thoroughly that, until 1906, Californians called it simply the Great Earthquake. Geologists at UC Berkeley have tracked the fault's last 5 major ruptures and found they occur, on average, every 140 years. Count forward from 1868, and you land in the past. We are already 18 years beyond that average, sitting in the zone where the next rupture becomes statistically expected, not just possible. That average carries real uncertainty, roughly 20 years in either direction, so overdue doesn't mean imminent. It means the fault has entered the range where history says a rupture becomes more likely, not that a date is written down anywhere. The Geological Survey puts a number on it: a 14% chance of a magnitude 6.7 or larger quake by 2034, rising to roughly 1 in 3 by 2043. That is the highest earthquake probability assigned to any fault in the Bay Area right now, higher, notably, than the nearby stretch of the San Andreas. And that's where the story should get complicated, because everyone still assumes the San Andreas is the dangerous one. That makes sense on paper. The San Andreas is the actual boundary between 2 tectonic plates. It's capable of a magnitude 7.5 earthquake or larger, bigger than anything the Hayward Fault alone could produce. That part is true. But in 1989, a magnitude 6.9 earthquake ruptured in the Santa Cruz Mountains on the San Andreas system, and even though it was strong enough to collapse a freeway and kill dozens, the shaking felt across the East Bay was comparatively mild. The epicenter sat in mostly empty mountains. The Hayward Fault doesn't have that luxury. It runs directly under the cities, which means the assumption that a bigger fault automatically means a bigger disaster just failed its first test. So if size doesn't decide the outcome, what does? Start with the fault's own surface, because Hayward hides a strange clue in plain sight. Parts of it creep. Slowly, continuously, without waiting for a big earthquake, sections of ground along the fault shift a few millimeters a year, cracking curbs, offsetting sidewalks, splitting foundations in a slow-motion tear. You can watch develop over a decade if you know where to look. Survey teams have chalked lines across some of these cracks just to track how fast they're spreading. For a while, that looked like good news. Creep releases stress gradually, in theory lowering the odds of a sudden catastrophic rupture. Researchers at UC Berkeley spent years mapping exactly how much of the fault behaves this way, and they found something less comforting. The creep isn't uniform. Some segments slide continuously and safely. Other segments, deeper and more critical, remain fully locked, storing energy with no release valve at all. The reassuring story about the whole fault quietly relieving itself was never true. It was only true for parts of it. Berkeley researchers isolated the difference by comparing satellite radar data along different segments of the fault. The northern stretch showed measurable creep. The section running beneath the densest parts of the East Bay showed almost none. In other words, the part of the fault most people live directly on top of is exactly the part storing the most unreleased energy. Next candidate, is this man-made? In parts of the country, earthquakes have been linked to wastewater injection, fluid pumped underground from industrial operations that changes pressure on existing faults and effectively lubricates a rupture. It's a real, documented mechanism elsewhere. But the Bay Area doesn't run that kind of large-scale injection program near the Hayward Fault, and the region's seismic pattern lines up with ordinary tectonic motion, the slow grinding of the Pacific Plate against North America. One explanation, ruled out. The driver here is natural stress, accumulating exactly where millions of people happen to live, which leaves the strangest possibility of all, the one that actually connects to the hook. In 2023, a magnitude 7.8 earthquake tore through Turkey and Syria. What made that disaster so devastating wasn't only the first rupture, it was what happened next. The shaking from that quake dynamically triggered a second, nearby fault within hours, compounding the destruction in a way seismologists are still studying. The physical idea is simple enough to picture. A large earthquake sends a pulse of stress through the crust, and if that pulse reaches a fault that's already loaded close to its breaking point, it can nudge the rupture forward, sometimes within hours, sometimes within days. Scripps seismologist Alice Gabriel has pointed directly at the Hayward Fault as a plausible candidate for the same kind of triggering if a large enough earthquake ever ruptures Southern California first. In other words, the next disaster on this fault might not start here at all. It could start hundreds of miles away, arrive as a wave of stress traveling through the crust, and finish the job on a fault that was already primed and waiting. That's not confirmed for Hayward specifically. Nobody can say it will happen or when. But the mechanism itself, dynamic triggering between distant faults, is documented, observed, and taken seriously enough that a leading seismologist is naming this fault by name as a likely candidate. Now bring back the ground itself, because it isn't finished complicating things. Earlier this year, teams at Lawrence Livermore and Lawrence Berkeley National Laboratories ran the most detailed earthquake simulations ever attempted for this fault, using some of the country's most powerful supercomputers to model 50 separate magnitude 7 scenarios. What they found wasn't just about where the fault breaks, it was about what happens to the shaking after it leaves the fault. Certain basins in the ground, bowl-shaped pockets of soft sediment like the one beneath the Livermore Valley, trap seismic waves and bounce them around, amplifying the shaking regardless of how close you are to the epicenter. A community that looks safely distant on a standard hazard map could still get hit harder than expected, simply because of what's sitting underneath it. That's still a simulation, not an observed event, because no modern instrument has ever recorded a full magnitude 7 rupture on this fault. But it means the older hazard maps that emergency planners have relied on for years may be underestimating risk in specific neighborhoods nobody flagged before. Turkey is the comparison that matters here, and it's worth sitting with for a second before pulling back. That 2023 sequence killed more than 50,000 people, largely because of building collapse in a region where construction standards varied widely and enforcement was inconsistent. The frightening part of the comparison isn't the death toll. It's the structure, a strike-slip fault, mechanically similar to Hayward, running directly beneath dense urban populations, with one section capable of triggering another. But similarity in structure is not a forecast of casualties. California rebuilt its earthquake codes after the 1989 Loma Prieta quake, and Bay Area retrofit programs have spent decades reinforcing exactly the kind of vulnerable wood frame housing that caused the worst losses in Turkey. The mechanism can rhyme without the outcome repeating. That distinction matters, and it's the one the evidence actually supports. There's a second comparison people keep reaching for, and it's worth shutting down clearly. The Cascadia subduction zone off the coast of the Pacific Northwest, capable of a magnitude 8.7 or larger megathrust earthquake with a tsunami attached. Some reporting has called Cascadia more dangerous than anything under the Bay Area, and that's probably true in terms of raw scale. But Cascadia is a completely different kind of fault, a subduction zone where one plate dives beneath another, not a strike-slip system like Hayward and the San Andreas. The two are not mechanically connected, don't share a trigger, and don't belong in the same warning. If you've seen headlines linking a Pacific Northwest megaquake to Bay Area seismic activity, that link is coincidence dressed up as connection, not shared physics. So, what does the actual record show once all these threads get separated out? Hayward isn't the biggest fault in California. It isn't the fault capable of producing the largest possible earthquake. What it is, uniquely, is the fault where an overdue rupture cycle, a documented pattern of uneven locking, a newly modeled amplification effect in the ground, and a plausible distant trigger all stack directly beneath the highest concentration of people in Northern California. That combination, not sheer size, is what moved it to the top of the list. Here's what's actually confirmed right now. The fault is roughly a century and a half overdue by its own historical average. Federal probability models put the odds of a damaging quake at about 1 in 3 within the next 2 decades. Supercomputer simulations from this year show specific basins could amplify shaking beyond older estimates. Sections of the fault creep, other sections stay locked, and a documented mechanism exists for a distant earthquake to trigger this one early. What's not confirmed is timing, and nobody studying this fault claims otherwise. Dynamic triggering from Southern California remains plausible, not proven. The basin amplification findings still need to be checked against a real rupture, something that has not happened in the modern instrumental record. Scientists are now watching creep meters and GPS stations for unusual deformation, tracking small earthquake swarms for signs of shifting stress, and waiting for the next geological survey probability update to see whether these findings move the numbers again. Any sudden clustering of small quakes along the locked segment, any unexpected jump in a GPS station's position, or any large rupture on a connected fault system farther south would immediately change how urgently that update gets written. None of that means a catastrophe is scheduled. It means the instruments keep recording, quietly, block by block, while a fault that already outlived its own historical clock sits directly beneath millions of people who have no idea they are standing on the answer to a question everyone's been asking about the wrong fault.